Hey guys, today we're going to do a quick trig review, and also talk about how trig is going to apply in the context of calculus. So I am going to post a couple of extra videos or reminders about things for this trig stuff. It's going to be a lot and it's going to go kind of fast. So if there's any piece that you need more help with, just go and look at those particular concepts for yourself. Okay, so the first thing we're going to talk about are exact trig values. And before I can get to that, I need to do some reminders about special right triangles. There are two special right triangles. Again, if it is a right triangle, that means one of the angles is a right angle. The first special right triangle is the 45-45-90 right triangle, which is also known as an isosceles triangle. And that means that both of the legs are the same. Now, we learned about all the little ratios that they take, and I try to make this as easy as I can for myself. And so if this leg is the 1, then that means that leg is also 1. And then if I do the Pythagorean theorem, this guy is the square root of 2. Okay. The other special right triangle that we learned about is the 30-60-90 right triangle. And this one has the ratios of the legs of 1, root 3, and 2. So in order to remember which side goes with which angle, the hypotenuse is going to be 2. It's the longest side of the triangle, the biggest angle. Across from the shortest side of the triangle, and the littlest angle is going to be 1. And then in between that guy is root 3. So there are 3 different side measurements for this one, and that's what the ratios are. Okay, that'll help us find our special trig values. Now, the other thing that we need to remember back from pre-cal is that we use these degree measures. They're great, 30, 60, 90, 45, 45, 90, but we use something called a radian also. Okay, the radians are great because they are unitless, so that way we can do a lot more analysis and application problems. And so the conversions you need to know is that a 30-degree angle is the same thing as pi over 6 radians. Okay, a 45-degree angle is the same thing as pi over 4 radians. A 60-degree angle is the same as pi over 3 radians, and then 90 degrees is the same as pi over 2. And if you remember, you have a unit circle, and there are multiples of those on the unit circle, but the only reference triangles that you will ever build are 30-60-90s or 45-45-90s. Okay, and then of course, just as a end all be all, we have our lovely SOHCAHTOA that we use in order to find our trig values. So if I was faced with finding something like the sine of pi over 3, the first thing I always do is plot this angle in the correct quadrant. Pi over 3 is the same thing as 60 degrees, so that's just in the first quadrant. Remember, the whole thing is 360 degrees or 2 pi. So if I make this, then this is pi over 3, that makes this a 60-degree triangle, and I just put these same ratios on each of the legs. So my hypotenuse will be 2, across from the 60 will be root 3, and then 1. And since I want the sine, I want the opposite over the hypotenuse. So that's going to be root 3 over 2. Okay, and that's perfect. You're going to see a lot of the same numbers pop up for these exact values. Same deal for the cosine of pi over 3. I actually have the same picture, right? I don't have to redraw it, thank goodness. My cosine is going to be my adjacent over my hypotenuse. So my adjacent leg is going to be 1. My hypotenuse is 2. That is the cosine of pi over 3. Same deal if I wanted to find tangent. Tangent is now the opposite over the adjacent. So for this guy, again, opposite leg is going to be root 3, and the adjacent leg is 1, so I could just leave this as root 3. If you are somebody who you didn't learn this with the triangles, you'd prefer to memorize your unit circle, by all means, go ahead and memorize your unit circle. Okay, there it is. You can Google unit circle. Okay, if you're using your unit circle, remember that sine goes with y, cosine goes with your x coordinate, and that tangent is like the slope of those two things, so it'll be y over x. So if I wanted to find the tangent of pi over 3, I'd go to pi over 3 on the unit circle, and I would take the y coordinate divided by the x coordinate. And that works for any of these. I know it might seem faster, but I forget my unit circle all the time. So no shame if you don't remember your unit circle. Okay, same deal if I'm given something like the cosecant of 11 pi over 6. Again, if you use your unit circle, I'm sure you're going to be like, that's straightforward, pretty good. Okay, it's 11 pi over 6. But what do you do with cosecant? Okay, so 11 pi over 6 is going to be in our fourth quadrant. and it is a over 6 angle, which means that this is a 30-degree angle. Again, pi over 6 is the same thing as 30 degrees. So if I label my triangle, that makes my hypotenuse 2, my opposite leg from the 31, and then root 3. Remember, though, if you're in quadrant 4, that makes this guy negative. Okay, that makes that leg it went down, it's negative. So the cosecant is the same thing as 1 over sine. So the easiest thing to do here is to either find the sine of this value and flip it over, or find the hypotenuse over the opposite leg. Okay, I tend to look for the sine first. So if I look at this guy, the sine of it is negative 1 over 2. So if I flip that all over, I'd get just negative 2. Okay, so again, cosecant goes with sine, secant goes with cosine, and cotangent goes with tangent. Okay, so this last one has 4 cosine of negative 5 pi over 4. Remember, whenever I'm going around the unit circle, I normally go around counterclockwise. So it gets bigger as you go around. If you have a negative, it just changes the direction that you're plotting. So instead of going up and around, I'm going to go down and around. So if I go down and around to negative 5 pi over 4, this would be 4 pi over 4. So 5 pi over 4 is in quadrant 2. Struggle bus. Okay, pi over 4 is the same thing as a 45-degree reference angle. So I can label my legs. Again, they're going to be the same. So I'm going to name them 1 and 1. Be careful what direction they're going. My hypotenuse is root 2. So if I'm finding the cosine of this, that would be my adjacent leg over my hypotenuse. Now be careful, there's a 4 in front. We're just going to leave that 4 in front. And now I'm left with negative 1 over root 2 for the cosine value. Okay, I'm just going to multiply straight across. Remember, this is 4 over 1, so that makes that negative 4 over the square root of 2. Sometimes you used to have to rationalize this denominator and change this into like 2 root 2 or something like that. Do not try to rationalize your denominators, okay? Leave them like they are. Don't make a mistake on doing something silly like a rationalize, okay? The last thing about exact values, if you remember this little mnemonic, all students take calculus. This tells you where your trig functions are positive. So everything's positive in 1, only sine and its reciprocal are positive in 2, only tangent and its reciprocal in 3, and only cosine and its reciprocal in 4. So that kind of can help you out. So you would know that if I was in quadrant 1 for these, they should be positive. Since this guy was in quadrant 4, only cosine is, so that means I knew that that answer should be negative, and same deal with number 5. Okay. The other thing that you might have seen a little bit last year in trig was solving these trig equations. Okay, the big thing about solving trig equations is you cannot just divide by a trig function. You can't just straight up be like, I'm going to divide this and then move on with your life. Okay, so the goal here is to try to isolate the trig function so then I can do an inverse operation just like you used to do with x. So my goal is to, again, get this trig thing by itself and then solve for x. So I'm going to subtract 2 from both sides. I get sine x is equal to negative 1. And so again, I'm trying to get x out of that inside. I want to know what angle gives me that sine. So I'm going to go ahead and do the inverse operation of both sides. So I'm looking for the angle that gives me this particular ratio. So if you're thinking about this, you can try to draw a triangle. The other tool that you might have seen, I hope you've seen, it helps me out a lot, is called the OIO chart. The OIO chart looks like this. You say OIO, IOU, oh, I don't owe you. Across the top of your chart, you're going to write SOHCAHTOA. And then these guys are going to be your quadrant border angles. So like you're going to use this angle, this angle, this angle, this angle. So I'm going to start at 0, then pi over 2, pi, and 3 pi over 2. So if I use my OIO chart, life becomes super straightforward. I want to know, where does sine equal negative 1? Well, in my sine column, negative 1 happens at 3 pi over 2 only. So that would be my answer for this equation. Okay. If I look at number 2, this one looks a little bit trickier. The goal here, though, is to, again, isolate x. So there's a couple of ways to do this. The way I would try to solve this is to try to just be dealing with trig functions. So I'm going to divide both sides by 2. And I'm left with sine x times cosine x equals 0. what this does for me is it tells me something times something else equals 0. Well, that must mean that one of these factors is equal to 0, just like when you do factoring problems. So I'm going to set sine x equal to 0, and I'm going to set cosine x equal to 0 and solve both of them. So again, at this point, I'm looking for where on my unit circle or what angle measure gives me a sine of 0. Well, if I go to my OAO chart, I have one at 0, have one at pi. Okay, I'll do the same thing for cosine. We have pi over 2 and 3 pi over 2. Pi over 2, 3 pi over 2. So basically, every single border angle will give me those answers. So the big thing to know here is that you mostly will get 2 answers on these types of questions, like most of the time. Okay, that first one was kind of not a fluke, but you don't see that quite as often. Okay, on this one, there's, again, a couple of ways that you could solve this. The first thing I would try to do, because I am just dealing with a trig function equals to 0, I would go ahead and take the inverse of both sides. So I'm going to go ahead and do the inverse sign to both sides of this equation. That leaves me with whatever's in my argument equals the inverse sine of 0. Okay, one of the things I didn't tell you as we're solving these, we were going to just solve these from 0 to 2 pi, just FYI. So when I'm looking here, I want to find where, either on my OAO chart or on my unit circle, where is sine equal to 0? Sine is equal to 0 at 0 and pi. So I'd have 0 or pi for my answers here. Now, the only thing is, if you notice, there's still a 2 attached over here. So I'm going to go ahead and divide both of those answers by 2. And that's going to get me that my answer should be 0, pi over 2. And there's your answers for those. Okay, so notice we're getting a lot of the same types of answers on these. As long as you can go forwards and backwards, you're doing a good job. Okay, I'm actually going to skip number 4. It has the same idea as number 3. If you wanted to try this one on your own, the answer is 0 and 4 pi over 3. But I did want to look at number 5 because this one looks a little bit scary. Again, I'm looking at this and I want to try to get all of the trig functions like by themselves. I'm trying to isolate the trig function. So imagine if this had said 2x squared minus root 3x equals 0. Well, what would I do? Oh, I'd try to factor. I could take out an x at both sides. Well, same thing here. I can factor out a cosine. That is a completely legitimate thing to do. I did not divide by a cosine. I just factored one out and I put it on the outside. Now it looks like this other problem where we said I have one factor and another factor. So in order for those things to be multiplied together and equal to 0, one of them must be 0. So I set each of my factors equal to 0. And then I solve them. Okay, so this guy I'm looking for, where is cosine equal to 0? I'll use my OAO chart. Cosine's equal to 0 at pi over 2 and 3 pi over 2. And then this guy, I still need to isolate the cosine, unfortunately. So I'm going to go ahead and add root 3 and divide by 2. So I'm looking for the angle who gives me that cosine value of root 3 over 2. If you're using your unit circle, please be careful. There should be 2 places where you have this value happen. 2 places where x is equal to root 3 over 2. If you're not using your unit circle, if you're thinking about this, you want a cosine value where your adjacent leg over your hypotenuse looks like this. If I use the Pythagorean theorem, I could find this last leg is 1. That makes this a 30, 60, 90 right triangle. So this should be a 30-degree angle. Okay, so pi over 6. Your other place where cosine is positive, all students take calculus, is down in quadrant 4. So again, that's a pi over 6 angle, and that one's 11 pi over 6. So there's a lot going on there when you're solving your trig equations. Just knowing your exact values is going to help you out so much. Okay, because we want to put trig in terms of calculus. So there are a couple of special trig limits that you need to know. And this is the guy that we really see a lot. We have the limit as x goes to 0 of sine x over x. So if I was to put this in my calculator and look at the picture, 3 days later it graphs. Oh man, I am zoomed weird. Here we go. So I don't know what this picture looks like normally, That's why I'm looking at my calculator, except for I'm also in the wrong mode. Man, y'all were like a video that is, well, nope, not going to work. Okay. I'm going to put this in radian so we can actually see what it's doing. So if you notice, you can see it's kind of going up and down, and then it makes that weird little hump, and then it does some things. If I zoomed in, one day it'll work. There we go. You can see that as x is getting closer and closer to that 0 value, y is getting closer and closer to 1. So this is an indeterminate form. If I was trying to plug in 0 into this equation, I would have gotten sine of 0 is 0 over 0. That's a problem. And I don't have any sort of ways to factor that. So we looked at the picture. I want to drag my picture. I guess I can't drag it. It's doing some weird stuff, but we go up until this one. We have like a squiggle. Oh, here it comes. Wow. I'm just going to freeze everything. That's fine. That's fine. It's going to squiggle around the sides, except for it's going to go up until it hits 1. So this is the limit you need to memorize. The limit as x goes to 0 of sine x over x is just 1. So what does that mean in general? Well, we are going to get ugly trig limits like these. And if I can get something in the form of sine x over x, I just know that that's going to go to 1 based on that property. So looking here, the limit as x goes to 0, sine x cosine x over x. Well, I know that when I'm doing a limit, if I have two things being multiplied together, I'm allowed to split them and do their limits separately. So what I'm going to do is split this sneakily and make sure that my sine x over x stays together because I know what that is. Okay, and then I'm just going to leave whatever else is left over here because I know this piece is equal to 1. So this is just going to be 1 times whatever this limit is. So I'm going to have 1 times the cosine of 0. If you look on your OIO chart, that is 1. So 1 times 1 is 1. Okay, so if I can find sine x over x, I'm excited. Now here, this one looks a little bit different. Okay, I have a sine of 4x over 2x. I need to have the same thing inside the argument that I have outside, like on the denominator. So really what that property says is it's like saying sine of something over that same something, that limit, x goes to 0, that limit is 1. So I need this to have a 4x on the inside and a 4x on the outside. It's really hard for me to change stuff on the inside. So I'm going to go ahead and, again, be sneaky and do something in order to change the outside of this function. I know I want my bottom to be 4, so I'm going to multiply by 2. Whenever I multiply in the denominator, I also have to multiply in the numerator. Okay? I'm just trying to make my argument match. So if I go ahead and do that, 2 times 2x is 4x. I have sine of 4x. And then I just have this 2 floating in the top. Okay? That's okay, because right here, this whole limit goes to 1, so I'm just left with the number 2. Okay, so we're going to use the same idea down here on number 3. Again, my goal is to get sine of something over the same thing. So if I notice here, I actually have 2 h's in the bottom. So I'm going to go ahead and split them up. Ooh, hey, okay. I don't know what's going on there. The limit is h goes to 0, sine of 2h, and I'm going to go ahead and split my denominator up. I don't like that fact there. So if I see I need a 2 in the bottom on this first half, so I'm going to go ahead and just multiply by 2 over 2. Remember, that's just like multiplying by 1. That makes all of this business all go to 1. So I'm left with the limit as h goes to 0 of 2 over h. So if I try to plug in 0 at this point, I get 2 over 0. That's a problem. Remember, there's an asymptote at that point. This is the point where I can say that this graph does not exist. Okay, this limit does not exist because this graph is doing that weird thing where one side is going up to positive infinity, the other side's going down to negative infinity. So this limit does not exist. Okay, we got one with a cosine and it's so scary. Okay, the goal here again, try to split stuff up. And what I see going on here in the bottom is I have a GCF. I have something in common here. I can factor the bottom into, take an x out, 2x plus 1. So if I split that up, I have this piece and this piece, and I can also split up my sines and cosines. Again, the goal is to make whatever this inside the argument of the sign be the same as the denominator. So I'm going to go ahead and put sine x over x. That gets rid of this, and then I'm left with 2 cosine x over 2x plus 1. So again, this piece goes to 1. If I plug in 0 into what's left, I have 2 cosine of 0 over 2 times 0 plus 1. That's 2 times 1 over 1, so just 2. Okay, again, all of these things I've been trying to plug in 0, and I end up getting 0 over 0. So the way that I'm changing my equation is, again, doing some sort of factoring, splitting up my expression so that way I have a sine x over x or something like that. Okay, so this last one, oh man, that was the worst line I ever could have drawn. Yikes. Okay, here we go. Oh, except for this is not part of it either. Okay, so I have the limit as x goes to 0 of cosine squared x minus 1 over negative x squared. Unfortunately, there's no signs in there. But there is one trig identity that if there's only one thing you ever remember from trig, it's that sine squared x plus cosine squared x equals 1. Okay, that's the Pythagorean identity. We use it a lot. So if I went ahead and I rearranged this equation to try to make it look like cosine squared x minus 1, I would get cosine squared x minus 1 is equal to negative sine squared x. Okay, all I did here is I moved stuff around until it looked like this. So I could go ahead and rewrite that numerator as negative sine squared x all over negative x squared. Nice thing there, we have a negative on top and bottom, so those two things turn into a positive. And now sine squared, remember all that means is I have 2 sines in the top, and then I have an x squared in the bottom, so I have 2 x's in the bottom. This goes to 1, this goes to 1. So my final answer is 1 times 1, or just 1.